Hello, this is Ed Chapman, and this video cast is going to focus on a simple question. Why are cells microscopic? If you think about it, all cells that we know about and that we have studied were invisible to humans until we invented microscopes that were powerful enough to see them. And before that point, we didn't know that living things were actually made of these tiny little compartments that we now call cells, thanks to Robert Hooke. So the question is, well, why aren't there cells of all different sizes? Why aren't there cells as big as beach balls or as big as tennis balls or as big as ping pong balls? Why are cells always so tiny? Well, there's a very simple reason for that, and that's what we need to explore in this video cast. Now, if you look at a large human cell, a human egg cell, which is one of the largest cells that humans produce, and you compare it to some common objects here, like maybe a coffee bean, a sesame seed, a grain of rice, or a grain of salt, you can see that a human egg is about a fifth the size of a grain of salt. So if you have really good eyes, and if the human egg cell is sitting on a dark background, you may just be able to see it without a microscope, but probably not. So it's right at the limit of our ability to see with what they call a naked eye, or an eye without any assistance of magnifying lenses. Now, the reason why cells are microscopic is all about the cell membrane. Okay, if you remember, cells are surrounded by a cell membrane. This is true for all cells, from prokaryotes and eukaryotes. And cells have to absorb material, primarily food and oxygen, especially in animal cells, from their environment. And at the same time, they have to get rid of or excrete waste products through this membrane into the environment. So there is this traffic into and out of the cell's cytoplasm through the cell membrane. And all this absorbing and excreting takes time, because absorption and excretion are happening mainly because of something called diffusion. And diffusion is a slow process. If you just have a little bit of distance to travel, diffusion doesn't take that long. But if you have a long distance to travel, it's going to take proportionally more time. Okay, so just to remind you guys what diffusion is simply the spreading of molecules from where they once were to where there were no molecules, or in other words, the spreading of molecules or atoms or whatever from where they were concentrated to where they were dilute. So, for example, if you put a lump of sugar in some water and you let it sit, the sugar molecules are going to diffuse into the water or dissolve. Okay, so diffusion makes material move through the cytoplasm, but it's slow. And the greater the distance material has to diffuse, the more time it's going to take. So because diffusion is slow, if a cell is tiny, like this cell, okay, we got a little cell here, it doesn't take very long for, like, say you have material out here, food molecules or oxygen atoms or something like that. These want to diffuse in. They only have to travel this far to get to the center of the cell. So the distance that they have to diffuse is only about that far, okay, not that far. But if a cell is larger, okay, if a cell is much larger, it's still going to have to diffuse materials in exactly the same way. But now they have to travel from here all the way to here to get to the center of the cell. And because diffusion is slow, it's obviously going to take a lot longer for material to make that journey from the outside all the way to the inside. Okay? Let me get back to where I was. All right. So large cells have a lot of trouble getting material all the way to their centers because the distance that diffusion has to move these molecules is large. So if you think of a cell that's living from moment to moment by using oxygen and using food and producing waste and having to get rid of that waste, cells that are too big to move this material by diffusion into or out of their cytoplasm, they're going to die. They're going to either suffocate or starve to death or choke on their own waste products. So we can mathematically represent this by calculating something called the surface area to volume ratio. To do this, you have to be able to calculate a number called area and a number called volume. And then what you do is you divide the surface area, or take surface area and divide it by volume. Okay, so we produce what's called a ratio. And all cells need a minimum amount of surface area per unit volume to survive. And remember that diffusion is slow, and the larger a cell, the more time it takes to absorb and excrete material. So if we assume, just for simplicity's sake, that cells are perfect cubes, we're going to pick this shape because cubes are very easy to calculate area and volume for. Okay, we can calculate surface area and volume. So for example, in this cube that's 1 centimeter tall by 1 centimeter wide by 1 centimeter deep, we can calculate the surface area by multiplying the height times the width, okay, which is 1 times 1. So each face of the cube is 1 square centimeter, and cubes have 6 faces, so 1 times 6 is 6. So the surface area of this cube is 6 square centimeters. And the volume, of course, is going to be multiplying all 3 dimensions, 1 by 1 by 1. So the volume of a cube is going to be equal to 1 cubic centimeter, or 1 cm3. All right. Now, if we double the size of the cube, okay, we can then calculate the surface area for twice this. And you'll notice now that the surface area is going to be 2 times 2 is 4, times 6 is 24 square centimeters. And the volume is going to be 2 times 2 times 2, which is 2 times 2 is 4, times 2 is 8. So the volume is going to be 8 cubic centimeters. All right. So let's put this in a table. All right. So if we have the cell's size and surface area and volume, and then we divide the two in the fourth column here, we can do some simple calculations. So just like we did before, here we have a cell that is 1 by 1 by 1. We come up with a surface area that is 6 square centimeters, a volume that is 1 cubic centimeter. So 6 divided by 1 gives us a surface area to volume ratio of 6. But look what happens when we double the size of the cube. Okay, so now the cube is 2 by 2 by 2. The surface area goes up to 24 square centimeters. The volume goes up to 8 cubic centimeters, but the surface area to volume ratio is half the amount. So you can see every time that we double the size of a cube-shaped cell, we cut the surface area to volume ratio in half. And remember, we said earlier that all cells need a minimum amount of surface area per unit volume to survive. All right. So if we continue this process, doubling each time, you can see how the surface area to volume ratio gets divided in half. So if we say that a cell can only live if it has at least a surface area to volume of 3 or greater, then every cell that is larger than this doesn't have enough surface area per unit volume to survive, so it's going to die. All right? It just doesn't have enough membrane to service all the diffusion it needs to keep its deep inside cytoplasm alive. All right. So notice that the surface area to volume ratio decreases as the cell size increases. And if we assume that a cell needs a surface area to volume ratio of at least 3, then anything smaller will not be able to absorb or excrete materials fast enough. All right, so these cells that I put a little skull and crossbones by are too large to survive because diffusion is just not fast enough to keep their insides going. They're too small. Now, in real life, cells solve this problem in 2 ways. They either increase their surface area by folding their cell membrane into very complicated shapes, or they build compartments, or they have compartments floating around in their cytoplasm, which are made of membrane, so they increase their surface area without increasing their volume. So let me show you graphically what I'm talking about here. So here's a cell that we have folded. So notice now it isn't just a sphere, a circle. It's got these infolded areas which increase its surface area. All these areas here are adding surface area without contributing very much to the volume. Okay, cells can also add compartments. Okay, we're going to talk about these compartments in our next unit. They're called organelles. We've already talked about one compartment, the nucleus, but by adding these structures, cells can be large, but because they're increasing their surface area without increasing their volume, they are literally raising their surface area to volume ratio and are able to survive at larger sizes. All right. Now, prokaryote cells are tiny cells. They have lots of surface area because their cell membranes are relatively large. The area of their cell membrane is large compared to their volume, and they get along just fine, but they have to stay unicellular and they have to stay small because they don't have any compartments. Eukaryote cells are much bigger, 10 to 100 times bigger than prokaryote cells because they have added compartments and folds. And if you look at this picture of a cell, this is a cell taken from this lining of the small intestine, and you'll notice here that the cell membrane is much folded to increase its surface area for absorbing food, digested food, and it has lots and lots of compartments and inner folding compartments to increase its surface area hugely without increasing its volume. Okay, now there is a limit to cell size even with compartments and even with the folding that we see in eukaryote cells. And so the only way organisms can become larger is to become multicellular. Okay, and so here we have some very simple multicellular algae. These algae are arranged in strings or filaments. And here we have, of course, a cross-section of an aquatic plant called Elodea, and you can see the individual cells, a lot like what Robert Hooke saw in cork. And each of these little green circles are compartments we know as chloroplasts, and their job is to do photosynthesis. But the reason why organisms like cats and dogs and humans can be so big is because we are multicellular. We have kept our surface area to volume ratio high by having lots and lots of cells working together in tissues and organs. All right, I think that ends the slideshow. Thanks for listening, and I'll talk to you soon.